Welcome back. In today's video, we are going back to the basics and exploring the fundamentals of electricity. Whether you are new to the topic or looking to refresh your knowledge, this video is for you. Do you know about the basic unit of matter? The basic unit of matter is an atom, consisting of a nucleus at its center, which is made up of protons and neutrons, surrounded by a cloud of electrons. It is the smallest possible unit of an element that retains the chemical properties of that element. The nucleus located at the center of the atom contains protons, which have a positive charge, and neutrons, which have no charge. The electrons, which have a negative charge, are found in orbitals or electron shells surrounding the nucleus. These electrons are attracted to the positively charged protons in the nucleus, maintaining a stable structure through electromagnetic forces. The number of protons in the nucleus defines the atomic number of an element, and it determines the element's identity. Let's see about the electric current. Electric current refers to the flow of electric charge through a conductor, such as wire. It is the movement of electrons or positive charge carriers in certain cases in a particular direction within a closed circuit. Electric current is a fundamental concept in electricity and plays a crucial role in various electrical and electronic devices. Current is measured in units called amperes, and it is defined as the rate of flow of charge past a given point in a circuit. 1 ampere is equal to 1 coulomb of charge passing through a point in 1 second. Electric current is typically generated by various sources, including batteries, generators, and power plants. When a voltage difference is applied across a conductor, it creates an electric field, which exerts a force on the charged particles, causing them to move. The direction of current flow is considered to be from the positive terminal of the voltage source to the negative terminal, although in reality, electrons flow in the opposite direction. There are two kinds of current electricity: direct current and alternating current. Direct current flows in one direction continuously, like the current from a battery, while alternating current periodically changes direction, typically used in household electricity supplied by power grids. Electric currents have numerous applications, from powering electrical appliances and devices to facilitating communication through electronic circuits, and they are essential in various fields such as electronics, telecommunications, power generation, and transportation. Potential difference. Potential difference is a fundamental concept in electricity and electronics. It is a measure of the electric potential energy per unit of electric charge. In simple terms, voltage represents the push or force that drives electric charges through a circuit. When there is a difference in electric potential between 2 points in an electrical circuit, electric charges tend to move from the point of higher potential to the point of lower potential in an attempt to equalize the potential energy. Voltage is created by various sources such as batteries, generators, or power supplies. For example, in a battery, chemical reactions create a voltage difference between its positive and negative terminals, which causes electrons to flow from the negative terminal to the positive terminal through an external circuit. Voltage is a key parameter in electrical systems and plays a significant role in determining how electric currents behave in a circuit. It is one of the factors that influence the flow of electrons and, in turn, the operation of electrical devices and equipment. In mathematical terms, voltage is defined as the work done per unit charge moved between 2 points. The volt is the international system of units, or SI unit, for voltage, and it is equivalent to 1 joule of energy per coulombs of charge. In practical applications, voltages can be positive or negative relative to a reference point. Do you know about resistance? Resistance is a fundamental electrical property that codifies how much a material or component opposite the flow of electric current through it. It is measured in units called ohms. When an electric current flows through a conductor or a circuit, it encounters resistance, which reduces the flow of current. This property converts some of the electrical energy into heat or other forms of energy. Resistance is determined by various factors, including the material's properties, the dimensions of the conductor, and the temperature. It can be calculated using Ohm's law, which states that the voltage across a component or material is directly proportional to the current flowing through it, with resistance being the constant of proportionality. Let's study about the Ohm's law. Ohm's law implies that when the voltage across a resistor increases, the current through it also increases provided the resistance remains constant. On the other hand, if the resistance increases for a given voltage, the current will decrease. The resistance of a conductor depends on its physical properties, including its length, cross-sectional area, and the resistivity of the material. Longer conductors generally have higher resistance, while wider conductors have lower resistance. Different materials have different resistivities, which determine their intrinsic resistance. In circuits, resistors are commonly used components to deliberately introduce resistance and control the flow of current. They are essential in shaping electrical signals, dividing voltage, limiting current, and various other applications in electronic and electrical engineering. Resistors are available in various types, shapes, and sizes, each with its specific characteristics. They are typically made of materials with high resistivity, such as carbon, metal, or metal oxide. The resistance value of a resistor is measured in ohms. Resistors come in fixed and variable types. Fixed resistors. These are the most common type of resistors and have a specific predetermined resistance value that cannot be changed. They are used in many electronic circuits to set specific voltage levels, current limits, or to provide in biasing. Variable resistors, also known as potentiometers or trimmers. These resistors have an adjustable resistance value. They allow the resistance to be varied manually by turning a knob or using a screwdriver. Variable resistors are used in applications where resistance adjustments are required, such as volume controls in audio devices or turn-in circuits. Resistors have color-coded bands on their bodies to indicate their resistance value, tolerance, and sometimes a temperature coefficient. By reading the color code, one can determine the resistance value of a fixed resistor. The standard color code uses 4 or 5 colored bands to represent these values. Here's how to interpret the color code for a 4-band resistor. First band. The first band represents the first digit of the resistance value. Each color corresponds to a specific number. Black color represents the value of 0. Brown color represents the value of 1. Red color represents the 2. Orange, 3. Yellow, 4. Green, 5. Blue, 6. Purple, 7. Gray, 8. And white, 9. Second band. The second band represents the second digit of the resistance value. It follows the same color to number mapping as the first band. Third band. The third band represents the multiplier or the number of zeros to be added after the 2 digits. Each color corresponds to a specific multiplier. Fourth band. The fourth band represents the tolerance of the resistor, indicating the allowable deviation in the resistance value. It is usually as a silver or gold band. Silver represents the 10% plus or minus. Gold, 5% plus or minus. If the resistor has a fifth band, it represents the temperature coefficient, which indicates how the resistance value changes with temperature. The temperature coefficient is not as commonly used as the resistance value and tolerance. For example, suppose you have a resistor with the color bands yellow, purple, black, and gold. To interpret the resistance value, the first band represents the value 4. The second band represents the value of 7. The third band represents the multiplier by 10 to the power 0. The fourth band represents the tolerance, 5% plus or minus. So the resistance value of this resistor is 47 multiplied by 10 to the power 0, which is 47 ohms, with a tolerance of 5% plus or minus. Let's see about inductance. Inductance is a fundamental property of an electrical circuit and a key concept in the field of electromagnetism. It refers to the ability of a component or conductor to generate an electromotive force or EMF and voltage across itself when the current flowing through it changes. Inductance is measured in units called henries. Inductance is primarily associated with coils or solenoids, which are made up of one or more turns of wire wound around a core material. When an electric current flows through a coil, it creates a magnetic field around it. When the current changes, the magnetic field also changes, and this change in magnetic field induces a voltage or EMF in the coil itself. The induced voltage opposes the change in current according to Faraday's law of electromagnetic induction. The magnitude of the induced voltage is directly proportional to the rate of change of current and the number of turns in the coil. It is also influenced by the core material and its magnetic properties. The mathematical relationship between inductance, induced voltage, and the rate of change of current is EMF equal to the minus L multiplied by di by dt, where EMF is the electromotive force induced in the coil. L is the inductance measured in henries. Di by dt is rate of change of current with time. The negative sign in the equation indicates that the induced EMF acts in a direction that opposes the change in current. Capacitance. Capacitance is another fundamental property of electrical circuits and is a key concept in the field of electromagnetism. It refers to the ability of a component or system to store an electric charge when a voltage is applied across it. Capacitance is measured in units called farads. Capacitance is primarily associated with capacitors, which are passive electronic components designed to have a specific capacitance value. Capacitors consist of two conducting plates separated by an insulating material called a dielectric. When a voltage is applied to the plates, an electric field is established between them, causing the plates to store electric charge. The capacitance of a capacitor depends on several factors, including the area of the plates, the distance between them, and the dielectric constant of the material between the plates. The larger the plate area and the closer the plates are to each other, the higher the capacitance. The mathematical relationship between capacitance, charge, and voltage across the capacitor is C equal to the Q divided by V, where C is the capacitance in farads. Q is electric charge stored on the capacitor in coulombs. V is the voltage across the capacitor in volts. The capacitance determines how much charge can be stored on the capacitor on a given voltage. A capacitor with higher capacitance can store more charge, while a capacitor with lower capacitance stores less charge for the same voltage. Capacitors are widely used in various applications, such as energy storage, smoothing power supply voltages, filtering signals, and coupling or decoupling components in electronic circuits. They are essential for managing and controlling electric charge in electronic devices and systems. Capacitance also plays a crucial role in determining the behavior of capacitive loads and the time constants of RC circuits. And there you have it. We have covered the fundamentals of electricity, including resistors, inductors, and capacitors. If you found this video informative, be sure to subscribe to our channel for more exciting content. And don't forget to hit that bell icon to receive notifications whenever we release a new video. Thank you for watching. Let's meet with our next video.